Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Today I want to talk about problem 3 in the second midterm exam practice. This problem focuses on our understanding of weather systems. Question A. Which of the following features is not found in the source region of an air mass? And the correct answer is 4, mountains. For an air mass to form, we need a large body of air that's sitting stably over some time so that it can take up the characteristics of its surroundings. In the Arctic, that it can become very cold and dry. In the tropics, that it can become humid and moist over the ocean. If we're over mountains, we have a variety of conditions at the surface, and we're not getting a uniform set of conditions across the air mass. We're also going to have in mountains upward and downward flow associated with mountain breezes, and that's not going to allow a big regional mass of air just to settle down and assume a uniform set of characteristics. Air masses are generally found forming under high pressure systems, clear sky conditions where the air is falling. Under low pressure systems, the air is rising and we're getting condensation and all interesting things happening as they happen in a cyclone and a storm. So generally, air masses are associated with large, high pressure systems. As we get over the polar regions, we get out over the Pacific high. And when we look at the general circulation, we'll see some of these key places where air masses are found. B. Which of the following air masses is expected to have the densest air? Going into this problem, we have to think about what makes air dense or heavy. Air is colder when it's denser, and air can be drier when it's denser, because moist air is lighter than dry air, because water molecules are lighter than your average air molecule. And when they go into the air, remember that when you fill a volume of air with molecules, each molecule takes up the same amount of space regardless of whether it's big or small. So when you introduce moisture into the atmosphere, you fill the air with lighter molecules, and therefore a given volume of air becomes lighter or less dense. So in this question B, continental polar air masses are cold and dry, and therefore they're heavier than the other ones. Continental tropical air masses are warm and moist. They're very light. Maritime polar Atlantic air masses are cold and moist. Maritime polar Pacific air masses are warmer and moist. So the answer is 4. C. Which of the following best describes a front? The answer is 2, a transition or boundary between two air masses of different density. Temperature and humidity are part of what makes parcels more or less dense, but fundamentally it's about density. It's to do with both the humidity and temperature of the air mass. So 1 is incomplete, 3 is incomplete, and 4 air masses of different pressure is just wrong. D. An area of divergence aloft can occur when the answer is 3. Wind speed increases as the air moves along. Divergence means spreading apart of air. And so the mental picture here is to think about cars on the highway. As cars slow down, they pile up together, and that would be convergence and an increase of the amount of cars present, or the amount of air present. As cars speed up from each other, they separate from each other on the highway, and the density of cars, if you will, becomes less because the cars are more spread out. So in this case, an area of divergence aloft can occur when wind speed increases as the air moves along. Question E. For a surface anticyclone to intensify, which of the following must occur? And the answer is there must be convergence in the jet stream winds aloft. The reason for this is, remember that at the surface in an anticyclone we have divergence, a high pressure system in the northern hemisphere. Air is coming out from the central high. That air has to be supplied from somewhere. So aloft we have air coming together and downward to supply the air coming out from the central high pressure system. So we have divergence at the surface to support convergence aloft. Answer 2, that there's divergence aloft, is wrong. because we would have air coming out at the top and out at the bottom, where would the air get supplied from in the system. And the last answer, the jet stream aloft does not impact the cyclone. That is wrong. To understand the weather, we have to understand that the upper levels and the lower levels are connected to each other, because the air at the surface, as it converges and diverges, both supplies and is supplied by air moving in the vertical. The vertical motion is critical, and as we've seen in the course, vertical motion is largely what creates weather in terms of clouds and precipitation, because as air rises and falls, it has to either cool or warm, therefore create condensation. In the anticyclone case, air is falling. We expect clear skies, because in falling air, the air is warming, so there's no condensation. So we get clear skies associated with anticyclones, because we get convergence aloft and downward motion over the high. Question F. I'm going to turn the page here, but starting the problem, a schematic of a developing, what I call a textbook lower 48 cyclone, shows the meteorological features at the surface and the upper level. Figure 3A. So I'm going to turn the page to discuss the answers. We have two curves. We have A and B at the end of the blue curve, and B and C marking the ends of the red curve, and those mark the two fronts. We then have a bunch of little bubbles, A1, A2, A3, A4, A5, and A6. A1 is in the jet stream, A2 is the vertical connection between the jet stream and the ground, A3 is at the ground, A6 is at the ground, A5 is again the vertical connector, and A4 is up in the jet stream at the upper level. And so which curve represents a warm front? The warm front is designated by the red line with the little half biscuits. The half biscuits point in the direction of motion of the warm front. In this case, the warm front is moving upward in the figure, northward, if you will, if you think about this being a picture in the northern hemisphere. And so the answer is BC. Where is colder air underrunning warming air? And it should say warmer air. And the answer is at a cold front. At a cold front, cold, dense air moves across the surface and pushes up warm air in front of it, or underruns the warm air, and that's happening at AB. In contrast, at BC, at a warm front, warm air is overrunning cold air. Where is air falling? Air is falling at A2. Where is there an upper level ridge? That's at A1. Where is there a surface level high pressure system? That's at A3. And remember, all of these things are tied together. A1, A2, and A3 in this figure represent what's happening associated with the surface high pressure system. A4, A5, and A6 represent what's happening with the surface low pressure system, the low pressure system being the center of the cyclone. And so it's tied together as following. At A1, we have convergence in the jet stream aloft. The convergence gives us downward air. The air piles up in the jet stream, pushes downwards, and pushes down to A3 and outward from the surface level high. You'll notice that the ridge, A1, is a little bit upstream from the convergence, and so the ridge sits slightly to the west of the surface high pressure system. The answers for part 4, where would you expect thunderstorms in a narrow zone? That's happening along the cold front at AB, because remember that a cold front is more bull-nosed at its front. You've got cold, dense air pushing forward. You get a very abrupt transition at the front, and you push air up rapidly, and you get thunderstorms. At a warm front, it's a much more gradual transition if you go back into the book. And so at a warm front, you get a gradual transition with fog and stratus clouds. And so the stratus clouds occur along BC, and the fog occurs along BC. Go back into the mental picture you have from your diagrams. Going back to question G, In problem 3, the appearance of cirrus, CI clouds, is often used to forecast a change in weather associated with the arrival of a front. Briefly explain why. First of all, what are cirrus clouds? Cirrus clouds are high-altitude clouds composed of ice crystals. They form in all fronts as they form in rising air that occurs when warmer, less dense air rises at a front. So cirrus clouds are generally associated with all fronts. As the air rises, the air cools and clouds form. Thus, we always expect some kind of clouds at a front. Cirrus clouds form at the highest altitude where the atmosphere is coldest. They're ice crystal clouds. So we expect cirrus clouds to form at a front. The next question is, why do they get used as a forecasting tool? And the answer there is because at the high altitudes of cirrus clouds, the friction is much lower, if not negligible, compared to the friction at the ground. So the front is moving along with winds that are being slowed by surface friction. These cirrus clouds are now forming in high altitude where there's no friction, and therefore the wind speeds are higher. Wind speeds are generally higher aloft than at the ground, and so they get blown ahead of the front, and so they arrive as a harbinger of the front to come, and a front means a change in weather of some kind. So we know that there are significant changes in cloud cover, humidity, pressure and temperature, and wind with the arrival of a front. Traditionally, when forecasts were difficult to make, the arrival of cirrus clouds at night would be associated with a halo around the moon, and that would be used as a forecasting tool to say that the next day the weather was expected to change. The last question in this problem, H, a land breeze flows from land to sea at night. Briefly explain why this occurs. In your explanation, note the role of radiational cooling, vertical motion, the pressure variation at the surface and aloft, and the horizontal motion. There's a sense in the textbook that land breezes are discussed as sort of an afterthought, but there's a lot of good meteorology in the setting up of a land breeze as you think about pressure gradient forces and how we've thought about winds aloft, but also winds at the surface based on the kind of pressure distributions you get. So let's take this from the start. The first thing that happens that causes a land breeze to occur is that the land cools more than the water at night. Thus we get two effects. At the land surface there is high pressure because we get sinking air. And as you know from the ideal gas law, if you increase the mass, one of the effects you get may be that the pressure will increase. So air is piling up over the land because it's sinking. Aloft over the land, the air column is cooler and there is low pressure at any given altitude aloft. Remember, we've talked about how in cold columns at a certain altitude above the surface, the pressure is going to be lower than in a warm column. So we get pressure gradients aloft in the horizontal that are different than pressure gradients at the surface with the land breeze. There is a pressure gradient set up from sea to land aloft and from land to sea at the surface. So now we get a circulation cell where air is falling over the land, being pushed out to sea, rising over the sea and being pushed back to land. And that is the circulation cell that is the sea, that is the land breeze. The whole system, as I say, sets up a circulation cell so that the wind is resupplied. I just want to comment on this question. I have comments here about this. It's a small-scale wind system, but it also illustrates some big-picture questions about high-pressure systems. Over the great land masses in the winter, over North America and Siberia, particularly in the winter, high-pressure systems are very stable because they reinforce themselves. Because in a high-pressure system, you have sinking air. The sinking air causes clear skies. The clear skies allow the ground to cool even more and more through the winter. And therefore, the cold ground causes the air to get even colder, which causes even more sinking. And so this is why winter air masses over Siberia and North America are so robust and such a large part of winter weather, because all the dynamics of how high pressure systems form, yield clear skies, lead to radiational cooling, which then leads to denser air, which leads to more sinking of the air, feeds back on itself to give you a very robust weather feature. And so there's a big picture question here. It's not just a detail at the end of our discussion of winds about the land and sea breezes. Land and sea breezes are also an important part of life in maritime Alaska. We have land-sea contrast all along the coast.